Thank you, guys. Before I start off, I have a question for all of you. How many of us wait for days and weeks for our models to converge, right? Okay. Well, we definitely spend a lot of time babysitting our models. And my talk here is fast, deep, recurrent net training. So hopefully by the end of the talk, we have some idea about how we will address some of these questions. Okay. So the story of deep speech, and probably of all of deep learning, is this. You start out with a toy data set or a small data set, and then you find a model. You do model exploration to find a model that fits your data very well. That is, it has a low bias, and then you scale. You scale both your model and your data set to really crush that problem. Go from a toy data set to really crushing that problem. But what we often find is when we are training these deep networks at scale, it is often difficult to distinguish between bias problems and optimization issues. So you'll often see cases where your models hit a glass ceiling, and then you find yourself asking this question, is this a bias problem, or is this an optimization issue? What exactly do I mean by that? When I speak about model bias, a symptom of that is often underfitting. So you take your model and you try to train on your data, and like this blue curve here, where we are plotting a cost function against the number of iterations of training, you see that this model is just not able to fit the data as well as some of the other models here. So this is symptomatic of underfitting, and you can say that this particular blue model has a very high bias. Of course, the deep learning solution to this problem is just make the model bigger, make the model deeper, right? On the other hand, you have optimization issues. Optimization issues often show up as nans. You try to train your model and you get just nans. In other cases, you also see curves like this where there's just no learning. It's just a flat training curve. Of course, deep learning practitioners are also quick to catch this and say, this is the case is that your learning rate is too high, and you should just drop down your learning rate, and maybe your model will look more like that, the orange curve. But you can already see here, the two problems both express their symptoms in the training curve, and it is often hard to distinguish between the two. Okay. So the point I'm trying to make here is when you're training these deep nets at scale, always keep in mind both the questions. We often think about bias and think about making the model bigger and bigger, but keep both the questions in mind. Is this model powerful enough to solve my problem? Can I make it bigger and bigger? And also, is there anything preventing my model from learning all the correlations in my data set? That is, can I make it easier for my model to learn from the data? So this talk is mainly about how we are addressing both these questions as we are hacking on deep speech, trying to solve the speech recognition problem. All the content in the talk is based on the amazing work of people at Baidu Silicon Valley AI Lab. My name is Sanjeev Satheesh. If you're looking for me in this picture, I'll just say I chose the wrong day to be working from home. Okay, so we'll basically start off with a quick introduction of what deep speech is, and then go over some examples of how we are trying to solve some of the bias issues and some of the optimization problems, and what are the big takeaways, high-level takeaways for us to take away from here. Okay, so deep speech is basically a deep network which reads in spectrograms of audio files, and the task that is given to the model is to transcribe what's in the audio clip. Okay. In a little bit more detail, deep speech is basically a deep recurrent neural network whose the input layer is a convolutional layer, so you can convolve filters across time to consume your spectrograms, followed by multiple layers of fully connected layers, and then a bidirectional recurrent layer. So the bidirectional recurrent layer allows the model to communicate information through time, both from the future and from the past. Immediately on top of that is a softmax layer. The softmax layer allows the model to predict one character at a time. So remember, the task is to go from spectrograms to characters. The spectrograms are read by the convolutional layers, and at the top is the softmax that predicts the characters. The whole model is trained with a sequence level loss called as the CTC loss. We'll just call it the CTC loss for now and not go into too much details. Okay, so that's deep speech version 1.0. What can we do to make it better, right? Of course, one of the great things we can do is to make it deeper, make it bigger, and see what happens. The point of making it bigger is to reduce the bias in the model, basically to fit the data even better and better. Okay, so this is what we did. Instead of having fully connected layers, we made all of them recurrent layers. Recurrent layers that are closer to the convolutional, that is the spectrograms, allow the model to communicate information at the input level, more data about the audio signals. And as you get closer and closer to the softmax, you can expect that this model is communicating more information about the orthography of the language and so on. Of course, you can see with one recurrent layer, this is what happens. And as you add more and more recurrent layers, you fit the data even better and better. So remember, all the graphs here are plotting the cost. Lower cost is better. So if you're fitting the training data better, your cost will go down. This is plotting cost on the training set, right? Okay, so you add more and more recurrent layers, you fit the data better and better until you hit a glass ceiling. You hit the glass ceiling and then you wonder, okay, looks like I have, so all these models have the same number of parameters. So once you hit the glass ceiling, you're like, maybe I should blow up my model, increase the size of my model, and add more parameters and see what happens, right? That's often the first thing we want to try. But the point of the talk is that you should also think about this other question, that is my model running into optimization issues, right? So let's see what we did in deep speech to address, to find out if there are optimization issues in this model. Okay, so the one thing that we tried is called Sorta Grad, which we'll go into a little bit detail now. The idea behind Sorta Grad is to improve the stability of training, which means fewer nans, fewer inf costs, and so on. Okay, the basic idea is this. In the first pass over your data, in the first epoch, you feed in the easy examples first, and as you go through your data set, you make the examples harder and harder. Okay, just like how you teach a baby. You teach a baby the easy examples first, mom, dad. And as it grows, you feed it more harder examples to learn from. The Sorta Grad idea is very much the same, except you do this only in the first pass. The insight is this. So the CTC loss is directly proportional to the length of your audio clip. So the longer your audio clip, the CTC loss is just going to be bigger and bigger. So you can use the CTC, the length as a proxy for how hard it is for your model to understand that clip. So the idea is you take the smaller clips first and you go through them in increasing order of length and you serve it in that sequence. Only in the first epoch. After the first epoch, you drop back to the standard SGD, stochastic gradient descent, where you sample uniformly from your entire data set. There's no sequence of sampling. Okay, so what happens? So we took a 7 bidirectional model, and we only changed the fact that we are now training with Sorta Grad. Remember, this means only that you have changed the way the first epoch, the data items in the first epoch is served. This we thought would be a stability-inducing thing, but it also ends up being an optimization trick which helps your model to train faster and to a better minima. This is important. Not only does the stability-inducing trick make the model converge faster, but it also helps converge to a better minima. And you'll see this trend over and over again. Okay. Let's move on to the second one. The second optimization trick you can try is batch normalization. This is a fairly popular method. This was first introduced in a paper in February 29 and was useful for getting to state of art on ImageNet. on the ImageNet challenge. The problem that batch normalization is trying to solve is reducing what is called as internal covariance shift. Now, what does that mean? Imagine a deep network, right? And just focus on one neuron, okay? Look at one neuron. As the entire model keeps training, the distribution of inputs into the neuron keeps changing. So you can see here, as this model it keeps training, the distribution of inputs to this nonlinearity keeps changing. What batch normalization is trying to do is, regardless of what distribution it is, it'll normalize that distribution to have a zero mean and unit variance. Okay? This is all what batch normalization is doing. This makes it so that the input distribution to any particular neuron at any point in training is consistent, so that that neuron is only looking at a stationary distribution. Okay. What happens here? So on top of just this 7 bidirectional model, we tried Sorta Grad, and then we tried batch norm on top of it. It helps fitting the data even better, right? So the cost is going down as we add batch norm on top of Sorta Grad. Okay. This, again, we thought is an optimization trick, right? This is what we expected this to help the model train faster. That is, we expected the convergence to be faster, but we really did not expect this gap in reducing the bias. This is another optimization trick that helps reduce the bias in the model. Oh, the blue lines here are basically saying that we only apply batch norm in the vertical connections. You can apply batch norm between any of the connections, but we only apply it in the vertical connections.
So the first batch norm is coming out of convolution?
Yes. Oh, yes. There's also a batch norm here. Good catch. I missed that line. So in every vertical connection is batch normalized. Yes. Okay. This is the question we've all been waiting to ask, right? All the models earlier on have been just using plain vanilla RNNs. Vanilla RNNs is just having anything that is not LSTM or variants of LSTMs, we can call them as vanilla recurrent networks. The idea behind using these LSTM cells or GRU cells is to let the gradient flow in some sense. We'll talk about that a little bit more now. Okay, a basic recurrent network looks like this. The interface is that it takes at time t an input and outputs a context vector h, and it also passes it to the next time step. So it's like you process an input and you have some state, and you want the state to be reused when computing the next time step. So this is what is the context vector. So this is what goes up and to the next time step. You can think of context vector as the state. What a vanilla RNN does is that it takes the state and completely overwrites it. This is a problem for two reasons. So if the RNN wants to pass state for more than one time step, right? Let's say it wants to remember some part of the state for more than one time step. It's really hard for the model, because the model already has this bias that I'm going to overwrite all the context vector, and it's very hard for it to remember the context for more than one time step. LSTM and GRU cells have fixed that by having a linear connection between the previous time step and the next time step. So HT is has also a linear dependence on HT minus 1. And the LSTM cells, by using this multiplication, control how much of my previous context to remember and how much to overwrite. So we explicitly model that this model can control how much to remember and how much to overwrite. And also, because this is a linear dependence and not passing through any squashing nonlinearities, we also get away from the problem of vanishing gradients. You can, basically, the idea is that you can think of this as an optimization trick, right? Okay. We use GRU cells here and not LSTM cells, because the LSTM cells typically are more flop hungry. They use more parameters, and they need more flops to compute to get the same effect. So if you can get the same effect with a simple cell, you should try it. There has been published research trying a whole bunch of variants of LSTMs, and they found that the GRU cells are about as good as the best LSTM configurations. Okay, so GRU cells you can think of as another optimization trick. Let's see what happens with that. So this is what we had. We had a baseline model with 7 bidirectional recurrences. We added Sorta Grad, better optimization to a better minima, on top of which we added batch norm, even better, and so the RNN cells can be swapped for GRU cells. We just did that, and it fits the data even better, right? These are all optimization tricks, remember. None of these are really bias reduction tricks, but we get that effect. There are a few more hacks like these in the paper, but I don't want to dwell too much on it. And let's get to the punchline. The punchline is make your model easier to optimize before scaling. Punchline really is make your model easier to optimize. So so you start out with a small data set. You're playing around, trying to find out which model fits your data well. And then as you scale, we will get into this problem that we'll hit a glass ceiling, and we won't know if we are fitting if we are having a bias problem or an optimization problem. So the point is, solve your optimization problems as soon as possible. So if you solve your optimization problems sooner, the idea is they're easier to identify. They will show up immediately in the first few thousand iterations in your training, and they're very easy to spot because literally easier to optimize means that you have a much sharper slope in the earlier iterations. And from all the examples we have seen here, they will make better use of the same number of parameters to fit the data even better. Okay? So remember, make your model easier to optimize before you scale. You can also think of this in a different way. Given a choice between 2 models, right? Which one do you pick? Regardless of which one you pick, you're going to hit this glass ceiling, and you are going to think, oh, I don't know if this is an optimization problem or a bias issue. So if you solve that problem much ahead, then it means that at least it's one less thing for you to think about later on. This rule of thumb is also a neat axis for reading papers. Let's say there are multiple papers trying to solve the same problem. It's one thing, it's easier to ask, is this model making it easier for me to optimize on this problem or that model? And also figuring out among all, there's usually many items in the paper, and finding out, oh, this particular trick in this particular paper is actually trying to solve an optimization problem and not really a bias problem or an overfitting problem, right? Then you can take only that part of the paper out and apply it on your model, and it'll probably help. So that's the main point. Focus also on making it easier for your model to optimize, not only which is often a very good way to reduce bias. Don't look at it only as a way of reducing bias. So that's it. Thank you so much. What questions do you have?
Yes, so the question was, how are you distinguishing between bias and optimization here?
The thesis is it's hard to distinguish between bias and optimization. You will hit a glass ceiling, and then you won't know if it's a bias problem.
What I mean is that you're saying that your model has some intrinsic bias,
yes,
and then you have the option to add some optimizations.
Yes.
How do you distinguish between saying, okay, adding GRU cells is an optimization rather than being an intrinsic part of the model? I just don't understand how you...
Oh, I see. So the GRU cells, for example, are particularly trying to solve the optimization problem of vanishing gradients. That's why I would put it more in the bucket of a general optimization trick than
So you're saying it's not an intrinsic part of the model, it's an addition?
Yes. Any other questions?
I was just wondering, as far as optimization goes, there are definitely architectural issues here, such as traditional RNN versus GRU versus LSTM. But have you guys looked into using a non-SGD optimizer, as in add a delta, or that basically optimizers that don't depend on the learning rate setting? There are plenty of those right now. Add a delta is kind of an old one by now for the stochastic-based solutions, but there's also VSGD by Jan LeCun, the No More Pesky Learning Rate paper, or actually add a secant from last year by Bengio.
Right. So the question is that in terms of optimization, there are a whole bunch of other optimizers as well that you could try. And we have only mainly stuck to the iterative stochastic gradient descent and variance of that. In this particular talk, we are using stochastic gradient descent with momentum and Nestrarov's acceleration. We did try a few variants. We tried Ada Delta and Ada Grad. They didn't perform as well. So we are basically sticking to SGD with momentum.
So Ada Delta is actually known not to perform super well, but for example, Ada secant and VSGD are supposed to be performing quite well. Same with Adam, although Adam depends on the learning rate a bit more.
I see.
Thank you.
That's definitely scope for us to explore further. We have only tried a few others, but not too much, I guess.
Yeah, I think actually optimization matters a lot. There was a talk by Jeremy Howard from Analytic and last year at Startup ML, and he basically demonstrated how they cut some training of the models that they're using, in their case CNNs, from weeks to hours, and by using different optimizers, and the convergence was to a much better optimum. So it seems like the whole problem, not just of setting the initial learning rate, but also of the weight decay, is really a black art, and better optimizers definitely take the headache out of that, and it seems like they're doing pretty well. So
I see.
I think I would trust Bengio, especially on this recent demonstration, and even LeCun's demonstration shows that you don't have to calculate the whole Hessian to have a pretty much optimal setting for the gradient, even in a stochastic setting.
I see.
And unlike Ada Grad, which has a continuous weight decay, so eventually your model stops learning. With VSGD, with LeCun's model, the learning rate goes back up if you have a shock to the model. So if the cost goes up, the learning rate goes up as well, which is pretty awesome in my opinion.
I see.
I think it's something to explore. So just an idea.
Oh yeah, absolutely. That's definitely a big pool of stuff that we haven't yet really explored yet. I'm definitely looking forward to looking.
One more quick question, or
Yes.
is that it? Do you have time for one quick one?
Absolutely, yes.
All right.
Yeah, I was wondering if you could describe a little bit what software you use, hardware.
Okay. So we have a follow-up talk from my colleague Shubho later today. I'm sure he can answer in detail a lot of these questions. As a quick summary, we use our own code base for optimizing for doing all of these optimizations. It's written from scratch using C++, CUDA, and MPI.
Okay, great. Let's have a hand for Sanjeev Satheesh. Thank you very much,
Thank you.
Sanjeev. The next talk will be at 2:10.